Thank you, thank you, thank you. All right, so today we're going to be looking at momentum, all right? Specifically at a couple of different types of collisions. I want you to see what happens in each type of collision, all right? Specifically what happens to momentum and what happens to energy, all right? So we've got a lab set up here. We've got a couple of carts. They're going to run into each other. They're going to collide in a couple of different ways, which I'll explain how we do that in a minute, okay? And my lovely assistants are going to help me out. Callista's running the computer a little bit here, and we're going to try to get some data and throw it up on the board and hopefully be able to show what we want. Now keep in mind that this is not a perfect situation. We do have friction. We've got other things going on outside, and so things will be a little bit off, but hopefully we'll be able to see what we want. Okay, here we go. So the red line is going to be this cart right here, okay, and the blue line is going to be this cart right here. And you'll see I'm going to give the red line, the first cart, a little bit of a push. It's going to run into this one, and then it's going to bounce off and go, all right? Now, right now, these two sides that are going to bump into each other are the soft sides of a Velcro, which means they're just going to kind of collide and keep going, all right? This is what we call an inelastic collision. All right, go ahead, Calista. All right, so now if you look at the data on Callista's computer here, right, you should be able to see right here, the first car started moving, and then right here is when it collided into the other cart, and then the blue cart started moving, okay? And so we've got, if you look at the velocity graph down here, you can see the velocity of the red car, the velocity of the blue car. So what I'm going to do down here is we're going to highlight this region where the velocity is constant. We're going to find out what the velocity was for that region right there. Okay, we can get the velocity by using our slope here. All right, and we're going to do it for just the first cart. All right, and we will get it, actually we want it for the top up here. So we'll highlight that top section. We'll get the latest position right there, and we'll get the velocity, which it is giving us a velocity of 0.332. All right, the blue one, we're going to get its velocity after the collision. Okay, and its velocity after the collision is hopefully pretty close to that. 0.2603. All right, so I'm going to put these two numbers up on the board. Okay, we've got our first situation, which I said was inelastic. Okay. Cart 1, before the collision, had a velocity of 0.336 meters per second. Okay. Cart 2, after the collision, had a velocity of, what was that number there, Calista? The blue one? The one that says slope? 260. Okay. Now we should also consider what velocity the red car had after the collision. So I'm going to get that too. So here's the red car after the collision, and the red car after the collision had a velocity of, right here, 0.055. All right, so V1 after the collision was 0.055. We're going to put that into some formulas here in just a minute. Okay, so we do have the masses of the two carts. Okay, the mass of cart 1 was 512 grams. Okay, mass 1 is 512 grams. And then mass 2 was also 512. So about the same size. All right. Now at this point we can find the momentum beforehand and we can find the momentum afterwards. All right. So we're going to go ahead and do that. So we've got the momentum beforehand, which was all in cart 1. So 0.512 because we want it in kilograms. So momentum equals the mass times the velocity. So 0.512 times its velocity, which was 0.336. All right, and if I pull out my calculator here,
it's on 56.
then I get 0.512 times 0.336, and I get a momentum of 0.172. All right, and then afterwards, we now have, both of them have some momentum. So we have 2, which was 0.512 times 0.260. And then cart 1 also had a little bit of momentum, which would have been 0.512 times 0.055. All right, so again, I'm going to go ahead and put both those in. 0.512 times 0.260, and then plus 0.512 times 0.055, and we're going to get a total of 0.161. Now you look at those two numbers, they're actually pretty close to one another. They're less than 10% off. And in an experiment like this, where we have some friction and some other real world things, we can accept that as that these two are close enough that we say, you know what, the momentum is the same before and after, because they're within about 10%. Okay, now if we look at kinetic energy, we're going to see something completely different. And so I want to look at the kinetic energy as well. Okay, so we're going to go kinetic energy is 1/2 mv squared. And so again, I'm going to go 0.5 times the mass, which is 0.512, times 0.336 squared. And I'm going to get 0.0289 joules. Okay, so that's my kinetic energy in the beginning. And then if I go over here to my kinetic energy end, I'm going to need to do 1/2 mv squared for each of those. And so again, I'm going to go 0.5 times the mass, 0.512, times 0.260 squared. And then I'm going to add 0.5 times 0.512 times 0.055 squared. And you'll see I ended up getting a kinetic energy of 0.01808. And you'll see that this is about half of what we started with. Where did the kinetic energy go? Well, the kinetic energy was lost in our collision because it was an inelastic collision. When the two things hit, there was a little bit of sound. You could hear it, right? When those two things hit, and you can see it again. There's a little bit of sound. There's some vibration going on. There's various things where the energy is lost in this collision, which is not an elastic collision. All right? So next, I want to show you a situation where it is perfectly elastic. All right, so now we're going to repeat the experiment, but this time I have two sides that when they get closer, they actually repel each other. They've got magnets in there. All right, and so I want you to look and see what's different this time as the two hit. Callista, can you come hit the green button for me again?
Okay, I'm getting ready. And I got it.
Okay, so again, we're going to send the cart. We'll stop it. You should be able to see the graphs there again. All right, and we're going to do the same thing that we did before. All right, we're going to get the momentum before and afterwards. So I've got my first car, the red car right here. We're going to go ahead and close each of these that we had before. We don't need those anymore. All right. So I'm going to get the velocity of the red car right here at the beginning. So we're going to highlight that. Okay, and get the slope there. Done. We're going to get the velocity of the red car after the collision. Okay, which is this one right here. So we'll get the slope again for car 1. Okay, and then we're going to get the velocity of the blue car after the collision. All right, and it says here on the graph, I hope you're noticing it says the velocity is negative, but we recognize that it's still going to the right. It's negative because it's going towards my second motion sensor over there. Okay, but we're going to count to the right as positive. So even though it's giving us a negative number, we're going to count that as a positive value. And so we're going to, for each of these, Callista, can you read off the number where it says slope there?
0.
Hold on just a second. All right. Yes, I'll have you do this one first. Whoa! All right, we're good. We're good. Okay, so this one first, then this one, and then that one, okay? Just the one where it says slope, all right?
Okay.
Okay, so read me the first one first.
0.5223 millimeters.
Okay, so this is the velocity of the first cart, which was 0.5223. 5223?
Yeah.
Okay, so 522. All right, and then the next one was the velocity of the first cart after the collision.
0.00071.
All right, now I don't know about you, but I'm pretty comfortable saying that that is basically at rest.
Okay.
What?
And there's a 2.
Okay, that's fine. That's fine. This is so small. This is less than a millimeter a second. That means it's not traveling very fast at all. So basically 0. Okay, so I think I'm pretty comfortable saying that's 0 within reason. Okay, and what was the blue one afterwards? The last number there.
0.5094.
All right, so again, I'm going with 3 digits, so 0.509. And I think you can already see this. Before I do any work at all, right, if I do the momentum beforehand, momentum equals m times v. So again, I have the 0.512 times my velocity here, which is 0.522. I get a momentum of 0.267. And then the momentum over here, if I say that's essentially 0, and then I have the 509 there, so 0.512 times 0.509. Again, we have 0.261. All right, so those two things are very close, definitely within 10%. So we can say, okay, yes, those two things look like they're exactly the same. So you can see again, in both of these situations, the momentum was approximately the same. So we can say the momentum is conserved. All right, now what we're going to look at is the kinetic energy. So again, we're going to go 1/2 mv squared. So I'm going to go 0.5 times 0.512 times 0.522 squared. And I'm going to get a kinetic energy of 0.0698. And that's the kinetic energy beforehand. And the kinetic energy afterwards is going to be almost the same thing, except I'm going to have 0.5 times 0.512 times 0.509. And that's going to give me 0.0663. And again, you'll notice, what do you see about these kinetic energies? Okay, last time when we did the inelastic collision, where they actually clashed, you had two energies, the 0.0289 and the 0.018, where this was almost half of that, right? In this situation, you'll see that the two energies are actually very, very close to each other. Again, within 10%, enough that we can say the kinetic energies here are the same. All right? And so in this situation where we said it was elastic, okay, if a collision is elastic, then the kinetic energies are conserved. Okay, so to review, here we said momentum conserved. We said kinetic energy not conserved. Okay, and then here, again, we said for the elastic, momentum conserved. And the kinetic energy was also conserved. All right, which was an interesting change. All right, I'm going to do one more set. All right, and this time I'm going to turn it around so we actually get the Velcro to match up. Okay, so this time when they hit, it's actually going to stick together. All right, Callista, can you come hit go for me one more time, friend? All right, so I've got it set up. We're ready to go.
I'm going to press in 3, 2, 1. No sensor connected.
No sensor connected. All right, maybe it got unplugged.
Nope.
got it. All right, now try Callista.
Studying collection now will erase the data.
Yes, erase.
Erase and continue.
And continue.
Ooh.
All right, let's see if we can do the same thing. We're going to get the velocities here. We're going to see if we can compare those two things. So right here, I've got cart 2 after the collision. Right here, I've got cart 1 before the collision. And you'll note this time that cart 1 had some significant velocity after the collision. So I'm going to make sure that I move this over here so that it is for sure after the collision. Alright, move this over. I'm going to move this over. Alright, Callista, can you do the same thing for me? Read this one, then that one, then that one where it says slope. Alright, so here we go. So first we're going to get cart 1 before the collision. Cart 1.
0.5259.
Okay, so we're going to go 526 meters per second. Alright. And then after the collision?
0.2457.
Okay, so we'll go 246 because I'm rounding to 3 digits. All right, and the cart 2, which is the last box there.
0.2538.
Okay, so 38, so 254. Thank you, Callista. Now, you'll notice that these two carts were stuck together. They were going the same speed, and yet the motion sensors were off by a little bit, right? Because they're off by a little bit, that's why we're okay with these, saying, you know, as long as it's within about 10% of each other, they're probably pretty close to the same thing. These two are the same thing. We know they were traveling together. So the fact that we got different values there kind of gives us an idea that, okay, the sensors aren't super duper accurate. All right? So we're going to go through and do the same process that we did before with this one. Okay? So we're going to do the initial momentum. Okay? So the momentum of the first one, which would be the mass, which is 0.512, times the velocity, which is 0.526. And we get a momentum of 0.269. And then I'm also going to do the momentum after the collision, so the mass of this one, which is 0.512, times 0.246. And then I'm going to add the momentum of the second cart, which was 0.512 times 0.254. And what I get is a momentum afterwards of 0.256. Now, those two numbers, again, are within about the same amount as those velocities were, right? So again, we can say these two momentums are basically the same thing, okay? A little bit lower. You'll notice the second one is always a little bit lower. The reason is because we are losing some momentum to the friction of the track, all right? It's not due to the collision. It's due to the track, so we are losing just a little bit every time, all right? But those two are close enough that we can say that during the collision, momentum is conserved. Okay, now let's look at the kinetic energy. Okay, the kinetic energy again is going to be that 1/2 mv squared. So I'll go back to the beginning. So I'll go 1/2 0.5 times 0.512 times the speed, which is 0.526 squared. And I have an initial kinetic energy of 0.0708. So that was initial. And then final, I'm going to do exactly the same thing, except I'm going to go 0.5 times 0.512 times 0.246 squared. And then I'm going to add the 0.5 times 0.512 times 0.254 squared. And what do you think is going to happen? What I think is going to happen is that I'm going to get 0.0320. Again, you'll notice this time this is actually less than half of the original kinetic energy. Okay, so this is what we call, when the Velcro sticks together and the two things link together, we call this perfectly inelastic. Okay, but the fact that it's inelastic, it means that the energy is not going to be conserved. All right, we saw in both our situations the inelastic and the perfectly inelastic, where it's stuck together. In both of those situations, momentum, yes, is conserved. It always is during a collision, but the kinetic energy was not conserved in both of those situations. However, if we have an elastic collision, then both the momentum and the kinetic energy will be conserved. All right? Now, the only other situation that we have is something that we call a superelastic collision, which we can look at one of those right now, okay? And basically in a superelastic collision, you have something internal that's providing energy, all right? Callista, can you click it one more time for me?
I'm starting at 3,
Yeah.
2, 1.
So you see him right there, and there you go. So something internal happened that caused it to gain energy. At the beginning, they were both at rest, right? They were both at rest. There was no momentum. Something happened in the middle that allowed them during this connection to gain kinetic energy. I'm not even going to go through this one, okay? But you should be able to recognize kinetic energy is definitely not being conserved, all right? The momentum will still be conserved, all right? In this situation, you saw this car flying this way. The other one didn't fly the other direction because my finger was on it, holding it in place. All right? But hopefully what you recognize and what you can see is that in a superelastic collision, you're going to be gaining kinetic energy. We started with none. We ended with a bunch. Okay? But momentum will still be conserved. All right? That's all I wanted to show you in this little lab. Hopefully you'll be able to take some of those ideas and apply it to the problem solving and other things you're going to do over the next little bit. Thanks, guys.